In this video, we're going to look at intervals of increasing and decreasing of a function. The first skill we need to develop is finding critical numbers of a function. The critical numbers of a function are when the first derivative is equal to 0 or it's undefined. Since this function is a polynomial, it's defined everywhere, but we do need to look for where the rate of change is 0. Our first derivative is 4x cubed minus 4x. This is equal to 0 and we can factor out a 4x. That leaves x squared minus 1 behind. Okay, so we have 4x times x plus 1, that's a difference of 2 squares, by the way, times x minus 1. Set each factor equal to 0. 4x is equal to 0 when x equals 0. X plus 1 equals 0 when x is negative 1. And x minus 1 is 0 when x is positive 1. These three values of x represent either a hilltop or a valley floor in your function. It's basically the same thing as we did a few videos ago where we found horizontal tangent lines. Those are the three values of x where a horizontal tangent line occurs. They're also important in helping to find cutoff values from increasing and decreasing intervals on a function. Now in this next example, we're going to find the critical numbers of the function, but we're also going to find the open intervals on which the function is increasing or decreasing. That's a rate of change that involves derivatives. Let's take our first derivative. That's equal to 0 when x equals 4. Okay, so that's your critical number. That's either a hilltop or a valley floor. Your graph, negative 3x squared plus 24x, we know if you were to graph that on a graphing calculator, is hill-shaped. It's a parabola that opens downward. After you find your critical number, if you're asked to find intervals of increasing or decreasing, mark off your critical number, or on the next example, critical numbers, and pick a test number from each side of that critical number. Something smaller than 4, something larger than 4. Plug this into your derivative because that will tell you the rate of change in this part of the graph. Our derivative with 0 subbed in. Now truthfully on here, it's cool to get a numerical value. Basically, you are looking for whether your answer is positive or negative. If your answer is positive, your graph will increase in that interval. The other side of 4, we picked 5 as a test number. The rate of change, when x is 5, negative 30 plus 24, that's a negative value. That means our function is decreasing in that interval. So to put it all together, as long as your values of x are less than 4, your graph is increasing. The moment you go past 4, your graph drops off and decreases. Remember, at exactly 4, you're at the hilltop. This function goes from increasing to decreasing, so you can kind of tell up here, if you were to round that off, that you would have a hilltop. We're going to find that in the next video, those actual locations of maxima and minima. But for now, we're just looking at intervals of increasing or decreasing. Let's look at the next example. It's going to be just a repeat example of this type where we find critical numbers and the open intervals on which the function is increasing or decreasing. So when you're asked to find that, the first thing you go after is your critical numbers. Our first derivative is 3x squared minus 3. Critical numbers occur when that's 0. Add 3 to both sides. Divide by 3. And then using square root property, you take the positive negative square root of 1. Well, that's positive negative 1. So this function has two critical numbers. Usually the way a cubic behaves is you'll have a hill and a valley. Not always, but a lot of the times you do. But at negative 1 and positive 1, there will either be a hilltop or a valley floor. That's what a critical number signifies. We're going to draw another number line, but we're also going to mark off those critical numbers. Like we did on the previous problem, we're going to pick test numbers from each little area. Something smaller than negative 1, something between negative 1 and positive 1, and then something larger than positive 1. You pick a test number from each interval separated by your critical numbers. We want to know the rate of change, so that's going to go into the derivative. Okay, so for this first interval, f prime of negative 2, that's 3 times negative 2 squared. And again, that goes into the derivative for rate of change. Using your calculator, you should get ballpark 9. Let's see, 4, 12. Yeah, the answer is 9. All we really need to know is if it's positive or negative. Move to your next test number. Let's get the rate of change in that middle section. A little quick math, we get negative 3. Again, the sign is all we need. And finally, our third test number is in that third open interval. 3 times 2 quantity squared. Actually, just the 2 squared. I misspoke. Anyway, that's 4, 12, 9, positive. That's all we really need to know. Okay. Let's step back and survey this. Our derivative was positive in 2 of the 3 intervals. The interval before our first critical number, also the third interval, the interval after our second critical number. That is these two. And then the middle area or interval, we had a negative rate of change, so that means our function decreases between the critical numbers.